Hi everybody, welcome back. We're going to look at section 3.4 and that is on increasing and decreasing intervals. So the paragraph up at the top says suppose that y equals f of x is a function defined on an open interval from a to b. In this lesson we will investigate what happens to the y values of f of x as the values of x increase. In other words, we will be able to determine when a function is increasing, means it's going to have a positive slope, and when the function is decreasing, which means we're going to be looking for negative slopes. All right, so today what we're going to do is look for open intervals where a function is increasing and decreasing. We're going to look for just the x values where we have horizontal tangent lines. And remember, a horizontal tangent line is where the derivative of your function equals 0. Okay, that's important. That's how we're going to find those. And then we're going to define which part of the function is increasing and decreasing by giving those intervals. Okay? So everything today is going to revolve around derivatives, which is what we've been learning. So all of the rules, all of the shortcuts, all of the chain rule, product, quotient rules, we're going to be pulling from today to get these derivatives that we need to look at. Okay? All right, so some of the concepts definitions. So first off, if you have a function on an interval from a to b, so you're just looking at part of the function, then we say that the function is increasing on a to b, okay, if x sub 1 is less than x sub 2, which implies that f of x sub 1 is less than f of x sub 2, for every x and x1 and x2 in that interval. Okay, so basically we know functions are increasing, okay, going up from left to right. So if x1 is less than x2, again, simply looking at the number line. So we have x1 to the left of x2, and these are the y values. So again, if we're going this way, then f of x sub 1 would be less than f of x sub 2 because we are increasing. So these are just telling you that when the x's when x2 is greater than x1 from left to right, then the same thing's going to happen with the function value. So basically, your function would be going up like this. And on the other end, we have decreasing, okay? So if if x sub 1 is less than x sub 2, okay, the x's implies that this is the other way. If f of x sub 1 is greater than f of x sub 2, so that means your function would be going like this, so that would be where it's decreasing. Okay? And we know we can look at a graph and see that, but today we're going to be looking at the functions and their derivatives to help us do that. All right, so number 2 just basically says that positive values for the derivative positive values for the derivative indicate positive slopes for the tangent lines, which in turn implies that the function is increasing. Okay, so we're going to look for where the derivative is positive. That's where your function would be increasing. So remember, we're going to be asked about where the function increases and decreases, but to do that, we're going to actually look at the derivative of that function. Okay, so this is the derivative, not the function. And then the same thing on number 3, negative values for the derivative indicate negative slopes for the tangent lines. So that would be where the function decreases. So that's where your derivative would be less than 0. So remember up here, we have horizontal tangent lines when the derivative equals 0. Okay? And then the other two sides of that is where is the derivative greater than 0 or less than 0. So greater than 0 is where your function's increasing. If the derivative is less than 0, that's where your function is decreasing. Okay? And this becomes very evident and it's very consistent throughout all that we do. So you'll get the hang of this. So don't panic yet that you see all of this stuff. It's not too bad to figure these out. And we're going to be using number lines to help us do that. And again, finding the derivatives, as long as you can do that, we should be okay. All right, so number 4 says, suppose that f of x is differentiable on an interval from a to b. Okay, so we've already talked about this. This is just another way to say that. If f prime of x is greater than 0 for every number between the a and b on that interval, then f is increasing. If the derivative is less than 0 for all those x's on that interval, then f is decreasing. So again, pay attention. Derivative is greater than 0, function is increasing. Okay? Derivative is less than 0, the function is decreasing. All right, and lastly, number 5 says the value of x for which a function is increasing or decreasing are always presented as open intervals. And then we're going to use the x-axis. Okay, so that's important. And as we go through these problems, I'll keep mentioning that to you. So hopefully that'll kind of sink in of what kind of intervals you're given. But the fact that we're doing open intervals, that's nice. So you don't have to worry about whether it's a parentheses or a bracket. For everything you give me with increasing and decreasing, you're going to be using parentheses because it's always going to be open. Okay? All right, so we're going to start by just looking at a function itself and just listing the intervals for where they're increasing or decreasing to make sure you understand that part of it. Okay, then we'll get into the derivatives. So for number 1, part A, it says, consider the graph of the function below. Determine the intervals for which this function is increasing and where it's decreasing. All right, so remember that where it increases is where your pen goes up from left to right, and then where it decreases is where your pen goes down. The place where it changes from increasing to decreasing, those are either going to be max or mins. Okay, those are the max or min values of your graph. So here and here, those are 2 points on my graph where I change from increasing to decreasing. All right, remember if you see an arrow on the left, that means that the x value is going to negative infinity. And when you see an arrow on your right, that's where x goes to positive infinity. So over here, this is saying that x is going to negative infinity, and on this side, x is going to positive infinity. Okay, because remember, we're doing the x values. We don't care about the y. That also means y is going down. Yes, this also means y is going up. But we're talking about moving on the x-axis to do these intervals. So this means that no matter where I am on the x-axis, I still have a point on the graph. So we're looking at x's. Okay. All right, so where is my graph increasing? Well, it's increasing from negative infinity until I get to this x value of negative 4. So my function is increasing. And I guess I'll say f of x. This is the function. Okay, f of x is increasing from negative infinity to negative 4. And then it's also increasing from positive 4 till I go to positive infinity. Okay, so that's where my pencil's moving up. The function is decreasing, okay, between here and here. So that would be between negative 4 and positive 4. That's where we're decreasing. So remember, always using open intervals and always using the x values, okay? Never use y when we're talking about increasing and decreasing. And the reason why, remember, because at negative 4, we change from increasing to decreasing, so it's doing neither at that point. That's a change up, okay? So that's why we're always going to use the open intervals. All right, let's try the next one. Okay, part B. So if you look at this graph, this represents x going to negative infinity over here. This arrow would represent x going to positive infinity. And then on this graph, from negative infinity, my pen is going up the whole way. So this function is only increasing, okay, from negative infinity to infinity. It's not going down anywhere, okay? So decreasing nowhere, if you want to write that. Okay. So that graph is just going up. All right, and let's look at the last one. This is an absolute value function. So again, this arrow represents x's at going to negative infinity. This arrow, that's positive infinity. So we're going down till we get to this point right here, which is at x equals 2. So this function decreases. Doesn't really matter the order you put this, just answer, and Hawks, make sure you're answering it the right way. So I just do it from left to right. So first we're decreasing here, we're going down from negative infinity to 2. And then we would increase on the other side. Okay, from here, starting up, we're increasing, so that would be from 2 to positive infinity. Okay? All right, so just getting used to the notation and making sure you're using the x values, not the y values. All right, so let's talk about the derivatives then and how we're going to do that. So for number 2, we're given a function and it asks you to find all the values of x that correspond to a horizontal tangent line. Well, remember, a horizontal tangent line is where the derivative actually equals 0. So all you have to do is find the derivative, set it equal to 0, and solve for those x's, right? We're looking for just the x's. Okay, so we're going to find the derivative, which is just using a power rule. So derivative of x cubed would be 3x squared. The derivative of negative 12x is minus 12. Derivative of 1 is 0. So we're going to take the derivative and set it equal to 0, and we're going to solve this, okay? Solve for x. So the first thing I'm going to do is divide everything by 3. Divide this by 3, this by 3, this by 3. Let's make it simpler for us. So if we divide by 3, we get that. 3 divided by 3 is 1. 12 divided by 3 is 4. 0 divided by 3 is still 0. Factor that. We get x plus 2, x minus 2. That's the difference of squares. Solve for that. So we get x equals negative 2 and x equals positive 2, right? Set each factor equal to 0 and solve those. So set x plus 2 equal to 0. Solve it. That's how I got x equals negative 2. Set x minus 2 equal to 0 and solve that one. You get x equals 2. So there are the two values where the derivative equals 0. So those are the x values of the function where there's a horizontal tangent line. Okay. Remember, horizontal tangent line simply means that when you draw your tangent line, it's going to be horizontal. Okay. So if this is a cubic function, and I know that it looks something like this. So what this is telling me is that this point is negative 2. That's a horizontal tangent line. And this point is negative 2, and then this point is 2. Okay, horizontal tangent line. Every other tangent line on this graph would be diagonal, would be slanted. Okay, all right. So now part B says use the values from the problem above, so in part A, and find the intervals where your function is increasing and decreasing. So it says use this first derivative number line and test points. Okay, so let's remember from part A, get that up here. We found that negative 2 and 2 were where the derivative was 0, horizontal tangent lines. So you're going to take a derivative number line. So I always put f prime, and you're going to put the 2 spots where your derivative equals 0, because those are boundaries. Those are the only 2 places where the derivative equals 0. So that means every other place up here, our derivative is either going to be increasing or decreasing, right? Positive or negative. All right, so we're going to pick test points, and we're going to put the test points in the derivative, not in the function, because we're testing the derivative. So a test point over here on this side would be negative 3. A test point in this area would be 0. That's always easy. And then a test point over in this area, maybe positive 3 or 4 or 5. You can pick any number you want as long as they're in the right spot. So you're going to take negative 3 and put it in the derivative. I always use the factors. You can plug it in here too. That's perfectly fine. Okay. So I'm going to take negative 3 and plug it in. Actually, any one of these doesn't matter. As long as you're putting it in one of the equations for your derivative, you're fine. I'm going to put it in here because it's easy for me to see what's positive and what's negative. So negative 3 here, negative 3 plus 2 is a negative 1. And negative 3 here, negative 3 minus 2 is negative 5. So a negative 1 times a negative 5 is a positive number. So I'm going to put a plus sign right there. Because when I put negative 3 into my derivative, I've got something positive. If I put it in here, just be careful. -3 squared is positive 9, and 9 minus 4 is 5. That's a positive number. Same thing. All right, then I'm going to try 0. If I put 0 in here, I get 2, and this is -2. When I put 0, 0 plus 2 is 2. 0 minus 2 is -2. And 2 times -2 is a negative number. I don't really care what the numbers are. I just care whether they're positive or negative. Again, if you put 0 in here, 0 squared is 0 minus 4 is -4. Still get negative. And lastly, pick something over here on the right side of 2. So I pick 3. So if I put 3 in here, that gives me a positive 5. And if I put 3 in here, I get a positive 1. So a positive times a positive is positive. Okay. So we tested these numbers and found that everything to the left of -2 was positive. Where your derivative is positive, I use an arrow because that means the function is increasing. Okay. Where the derivative is negative, that means your function is decreasing. And where the derivative was positive, again, that's increasing. So when I'm looking for where my function is increasing, I want the plus signs, which is the up arrows for increasing, down arrows decreasing. So f of x, the function, is increasing where the derivative was positive. So between, or from -infinity to -2, and from 2 to infinity. Okay, that's where my plus signs work. And then the function is decreasing where the derivative was negative, so between -2 and 2. Okay. But notice I did my test points here. So again, that graph that we looked at here, now I know, this is -2, this is +2. And look, it was increasing from -infinity to -2, and it was also increasing from 2 to infinity, decreasing in here. So I didn't really need to see this graph because the derivative told me that, but just so you could kind of see how it worked out. Okay. All right. So let's look at the next one. Now, number 3 gives you the derivative, not a function. Suppose the derivative of function f has already been found to be this. Okay. Find the values of x that correspond to a horizontal tangent line. So we already have the derivative. So be careful with the notation. You don't have to find the derivative. This is the derivative. So we just need to take this derivative and set it equal to 0. Okay, so be very careful. In number 2, you were given f of x, so we had to find f prime. But in this problem, they're giving you the derivative. So we just need to take the derivative and set it equal to 0. So again, to make this easier, I see that all these numbers are divisible by 4. So divide this by 4, this by 4, this by 4, this by 4. So that'll give you x squared plus 2x minus 15 equals 0. Remember, 0 divided by anything is still 0. So now we can factor that much easier. So we can factor that. Factors of 15 that give you 2 would be 5 and 3. Okay, set each factor equal to 0 and solve. So you're going to get on this one, x equals -5. And on this side, you'll get x equals 3. Okay, so those are the two values where you have a horizontal tangent line. Okay. Now part B, just like we did above, we're going to find now where this function, even though I don't have the function, doesn't matter. Okay, I don't know what the function is, but I know its derivative. So I can find where the function is increasing and decreasing because I know this. So we're going to take where the derivative equals 0 on the number line. So at -5 and 3. So I know that's where the derivative equals 0. So now I need to know where is the derivative positive and negative. So that's where I need my test points. So pick a test point over here, -6. Pick a test point in the middle of -5 and 3, 0. And pick something bigger than 3. And again, it doesn't matter as long as you pick a number in there. I could pick 10, -10, doesn't matter. Okay. All right, so plug these into your derivative. So again, I don't want to have to plug it into here and work it out. That's why I always use the factors. You're welcome to use any one of these three lines is fine, but I find this to be the easiest because once I plug it in here, then all I'm looking for is, are these factors positive or negative, and I know how to multiply. Okay. So look at -6. If you put -6 in this parentheses, you're going to get a -1. And if you put -6 over here, you're going to get a -9. And so now I know I got a negative times a negative, which is positive. That's all I care about. Okay, I'm going to put 0 in this line. So if I put 0 over here, that's going to give me 5. And if I put 0 here, that gives me -3. And 5 times -3 is a negative number. And then I'm going to try 4. Plug 4 over here, that's going to give me 9. Put 4 here, that gives me 1. 9 times 1 is positive. Okay, so similar to the last one, to the left of -5, your function is going to be increasing because it's positive slope. In between -5 and 3, your function is going to be decreasing because you got a negative slope. And over here, but after 3, from 3 to positive infinity, we got positive number again, so that means we're increasing. Okay, so f of x is increasing from -infinity to -5 and from 3 to positive infinity. Remember, we're using the x values. These are the test points, so that's, be careful, okay? These were test points. They don't have anything to do with your intervals. These are your numbers that you need. These are the zeros, right, where the tangent was 0. All right, and then the function was decreasing on this graph in the middle, so between -5 and 3. Okay. All right. So hopefully that's, you're seeing that it's very consistent on how we do these, okay? What's different is going to be the functions you're given, and then that'll depend on all of these new rules you've learned in the previous sections. Okay, so number 4, find all values of x that correspond to a horizontal tangent line, and then find the open intervals where the function is increasing and decreasing. Use the first derivative. So now we're just taking the same directions that we had for 2 parts and making it just 1 part for you. So in 4a, you have a polynomial. So to find where the horizontal tangent lines are, we need the derivative, and we need the derivative to be equal to 0. So power rule, derivative of 2 is 0, so I don't need that. The derivative of the next term, the derivative of -4x is -4. And then the derivative of the last term, -2 times 2 is -4. Subtract 1, so we get -4x. That's what you're going to set equal to 0 and solve that. Okay, so I'm just going to take the -4x and bring it over here so that it's positive. So -4 equals a positive 4x. Divide both sides by 4. So we get x equals -1. So that's the horizontal tangent line is 0. Okay, so that's the first part. This is where the function has a horizontal tangent line at x equals -1. Now we're going to find where the function increases or decreases. So we're going to take the derivative number line, plug our horizontal tangent line. So we only have 1 there. So I only have to do 2 test points now. I need a number to the left of -1, a number to the right of -1. So over here, let's pick a test point of -2. And over here, let's pick a test point of, let's say, +1. Doesn't matter. Just as long as it's on the left side, the right side. All right, now I didn't have factors, so I'm just going to plug it into my function. Okay, doesn't matter. So if I plug in -2, be careful. -4 times -2 is +8. So -4 plus 8 is a positive number. So over here is positive. Okay. And then if I put 1 in here, -4 times 1 is -4. -4 minus 4 is -8. So this side is minus. So this side's where your function's increasing, and over here's where your function is decreasing. right? So wherever there's a plus sign, function is increasing. Wherever your derivative is minus, decreasing. So f of x is increasing from negative infinity to negative 1, and f of x is decreasing over here, so from negative 1 to infinity. Okay. So we got a horizontal tangent line right here, and then your increasing and decreasing intervals. Okay. All right, let's try B. So this is a chain rule, that general power rule we're going to use to find the derivative. So let's do that. So remember the general power rule from section 3.2. We're going to take, just like we do the power rule, bring the 2 out front, leave that the way it is, and subtract 1 from your exponent. So you get 1 there. And then you're going to multiply by the derivative of this inside function. So the derivative of 2x plus 3 is just 2, right? This derivative is 2, this derivative is 0. All right, so because we have to set that equal to 0 and solve it, we're going to clean that up a bit. So we're going to do 2 times 2, which is 4, times 2x plus 3. You don't need the 1 there. That's what you're going to set equal to 0 and solve. Okay? All right, so let's remove this 4 by dividing both sides by 4. Divide this side by 4, divide this side by 4. We get 2x plus 3 equals 0. Right, 4 divided by 4 is 1. And then over here we still have 0. Solve that now, that's much easier. So we're going to subtract 3 from both sides and divide by 2. So our horizontal tangent line for the function is negative 3/2. Okay, that's where x, that's where your function has a horizontal tangent line of 0 at x equals negative 3/2. All right, so then we just need to take our number line, put any place where you had that horizontal tangent line. So again, only 1 on this one. So we need 2 test points, something to the left, something to the right. So let's pick something to the left of negative 3/2. Okay, what would be a good number over here? That would be, I don't care, negative 5, let's say. Is anything to the left of negative 3/2? Negative 2, negative 3, negative 4, it doesn't matter. And then over here on this side, pick something to the right of negative 3/2. Let's pick 1. Test points don't matter what number you pick as long as they are in the right boundary. Okay, you're in the right spot. All right, so where are we going to put this? Doesn't matter. You could put it any one of these, but to me, this is the easiest place. So I'm going to put negative 5 right in here. So 2 times negative 5 is negative 10 plus 3. That's something negative, so it's negative on this side. Pick 1 over here. 2 times 1 is 2 plus 3 is 5. That's positive. So remember, you're testing these in the derivative. That's why I keep putting this here. You're testing the derivative where the derivative is positive and negative. That's telling you where the function is increasing and decreasing. All right, so I know my function is going to be decreasing over here and increasing there, right? Those are the signs I got. So f of x is increasing over here. So from negative 3/2 to infinity. And f of x is decreasing over here. So that would be from negative infinity to negative 3/2. Okay? So again, think about what we're doing. We're given a function, we're finding the derivative, finding the x value where the derivative is equal to 0. That's the horizontal tangent line. That's the boundaries. Those are the max and mins. And then we're taking test points around those horizontal tangent lines to see where the derivative is positive and negative, because that tells you where the function is increasing or decreasing. Okay. All right, I'm going to stop here and pick up on part 2 so that these aren't too long. So I'll see you back here in a minute to finish up number 4.